Can you hear me?
Yes, sir. Am I audible?
Your voice is too much low. Can you increase your voice, please?
Now, am I audible?
Okay, okay. Screen, can you full screen? Okay, thank you. You're welcome.
Okay.
You have 15 minutes and 5 minutes question section.
Okay, okay, sir. This is Debasis Haldar, PhD scholar of NIT Rourkela, India, and I am going to present my talk, Multiframelet and Multiframelet Set on QP. So these are the outlines. And the first, I will going to discuss about what is periodic number and the properties of this set of this periodic number QP and multiframelet defined on this QP, multiframelet set, and the references. First is for a prime number P, a field QP of periodic number is defined as the completion of the field of the resonance number Q with respect to the non-Archimedean periodic norm. This periodic norm is defined as it is a 0 when x is equals to 0, and it is p to the power minus gamma when x is equals to p to the power gamma times m by n, where this p doesn't divide m and n, and this gamma m n are the integers. So this norm satisfies the strong triangle inequality is this, and that is why this norm is said to be a non-Archimedean norm. So the canonical form of any the canonical form of any this periodic number x is the summation of xj p to the power j, where this j is from the gamma to infinity, and where this gamma is can be any integer, and these xj's are from the 0 to p minus 1, and the leading coefficient x gamma is not equals to 0. The fractional part of this x is defined as the summation of this xj p to the power j, where this j is from the gamma to minus 1. So the fractional part of this x is equals to 0 if and only the gamma is a non-negative, and the fractional part of 0 is 0. The set of periodic integers zp is defined as the set of all periodic number such that whose fractional part is the 0, and set of all the fractionals number ip is defined as the set of all periodic number x such that whose fractional part is the x, the number itself. A ball, a center at C with radius p to the power gamma is defined as this b gamma c, and is denoted as b gamma c and defined as the set of all periodic number x such that whose norm of x minus c is less equals to p to the power gamma. The set JPM is defined as the set of all the numbers. This is minus m p to the power minus m to the sum s minus 1 p to the power minus 1, and where these sj's are the this 0 to p minus 1, and the leading coefficient is minus j is not equals to 0. So the order of this set can be is the p minus 1 into p to the power m minus 1. The inner product defined on this L2QP is as the integration of fx conjugate complex conjugate of gx dx, and the measure is given here with respect to the Haar measure. The additive character, the chi p on the field this QP is defined as the x goes to e to the power 2 pi I, the fractional part of x. The Fourier transform of f is defined as the integration of this chi p x fx dx, and the inverse Fourier transform of f is defined as the integration of chi p minus x f dz. And there is a wonderful relation between the Fourier transform, between the function and its Fourier transform. It says that Parseval theorem. It says that inner product of f and g is same as the inner product of Fourier transform of f and g. So now the properties of the QP, the field of periodic number. So we are now going to present some of the properties of this on this set. The set of natural number n is dense in the set of all periodic number, is periodic integer, and set of all rational number is dense in set of all periodic number. This QP is a fraction field of ZP. This QP is locally compact, totally disconnected, and has no isolated points. Every ball BJC is both open and compact. Every point of the ball is the center of the ball. Any two balls in QP are either nested, means one is completely inside the other, or the disjoint. This QP with respect to addition and multiplication is a field with characteristic 0, and IP shifts of the ZP for the IP shifts of ZP will form a partition of this QP. Any set K is compact if and only if it is closed and bounded. Any number, any periodic integer x is invertible if its the periodic norm is equals to 1. Any series UN is convergent if its sequence goes to 0, and if the norm of x is less equals to norm of y, then this norm of x plus y is equals to norm of y. So any triangle is isosceles. Now the multiframelet of this QP. So for this these L many functions, f1 up to FFL of this L2 QP, and this factor L is defined as this finite set 1, 2 up to L. This affine system FLJA, where this FLJ is defined as the p to the power j by 2 FL p to the power minus j times x minus a, and this j is in integer, a is in the periodic fractional number, and the L is the factor L. This affine system is said to be a multiframelet of order L if there exist two positive constant a, b such that this condition, this equation 1 will satisfy. So this system, this affine system is said to be a baselet if only this second inequality of this equation 1 will satisfy. And this multiframelet is said to be a tight multiframelet if we can choose a equals to b, and it is said to be a normalized tight multiframelet if we can choose a equals to b equals to 1. Here this a is said to be the lower multiframelet bound, and b is said to be the upper multiframelet bound. So here are two examples of this multiframelet. The first one is the equation 2 is of multiframelet. This will produce a multiframelet of order p minus 1, and the second one will produce a multiframelet of order p minus 1 times p to the power m minus 1. So now we are going to present some of the properties of this multiframelet. So every multiframelet is complete in L2 QP. Means it's the closure of the span of this multiframelets will the L2 QP. Each of the element of this multiframelet with upper bound B are the bounded above by the root of the B, the square root of B. If this affine system, this FJL is a baselet for a dense subset, then it is a baselet for the whole space L2QP. And this this multiframelet, if it is a multiframelet for a dense subset of this L2QP, then it is a multiframelet for a L2QP. Means the to checking a baselet or a multiframelet is enough to check on the dense subset. The multiframelet sequence, a sequence this FJL is said to be a multiframelet sequence if it is a multiframelet for the closure of the span of this affine system. So the every multiframelet is a multiframelet sequence, and the every multiframelet sequence is a baselet. The FJL is a multiframelet sequence with bound, let's say AB, and if U is a unitary operator on this L2QP, then the unitary operator U applied on this the affine system will give you a multiframelet sequence with the same bound. And here this bound AB means the A is the it is understood that A is the lower bound and B is the upper bound. The multiframelet operator S is defined as by this the sum. So this multiframelet operator S is bounded, a linear, self-adjoint, and the bijective operator. So if this affine system is a multiframelet with bound AB, then the inverse of this multiframelet operator applied on this affine system is a multiframelet with bound the B inverse A inverse. The next one is the important result of this multiframelet. It is a multiframelet decomposition theorem. Let this affine system is a multiframelet for this L2QP with the multiframelet operator S. Then any element G can be written as this, like this, or by this, where the sum converges unconditionally. Next, we are going to present a multiframelet set. A measurable set, this factor F, is said to be a multiframelet set of order L if this factorial can be written as the union of this FL, where the Fourier transform of each of these FL is the characteristic function of capital FL, and this affine system will form a multiframelet for L2QP. And this one is an example of the multiframelet set, and this is a multiframelet set of order P-1. And
dear Professor Haldar, you have about 5 minutes.
Okay. And here is the example of this the normalized type multiframelet set. The next is let this affine system is a multiframelet for L2QP with the upper bound B, and the Fourier transform of this FL is characteristic function of this capital FL. Then the measure of this, if of this FL is less equals to B. And here is it is if this JL is a normalized type multiframelet, then these two conditions will be held. And let this be a system such that the fractional transform this the Fourier transform of this, then this the union of this in FL is a multiframelet set of bound EFAB if and only that this condition will hold. And the one is the similar kind of result. The semi-orthogonal multiframelet, if a multiframelet is said to be a semi-orthogonal multiframelet, if the closure of this span is the perpendicular with the this span, where this J and K are not equal to, and they are not equal. So here is a theorem on this semi-orthogonal multiframelet. If this is a system such that the union is a disjoint the measurable set, and if this is a semi-orthogonal multiframelet, this affine system, then means this form a measurable partition, and then it will satisfy this one means this relation. So these are the some important references. Thank you.
Professor Haldar, we thank you for your presentation.